So if I have 20 and 70 degrees, what do we know about them? What do we know about them? What is it? They both are in the first quadrant. That is true. That is one thing. If you saw them on your unit circle, they're both in the first quadrant. So they would both be the reference angle if we were looking for reference angles. They add up to 90 degrees. That's pretty important. So they have a name when they add up to 90 degrees. We learned it in chapter 1 of geometry. And it was on your essential question. You might have seen it. What is it? Complementary. Yes, they are complementary. Now, in a triangle, if I draw our right triangle, because you guys know study of trig is all about right triangles, 20 and 70 would fit in there, right? Because 20 would be an acute angle and 70 would be an acute angle. And those two acute angles add up to 90. And so your 90 plus the other 90 is going to give you 180. So those are perfect angles for a right triangle. So just labeling some sides. Let's say this is our little a. Let's say this is our little b. And always across from the right angle is our hypotenuse. We'll call that little c. Now let's review the 6 trig functions. Or let's actually just review the 3 of them. We know the other 3 are reciprocals. But if I wanted to find the sine of 20 degrees, I would need the opposite of 20. So SOH, right? This is the opposite over the hypotenuse. That's what sine means. Opposite over hypotenuse. So if I'm looking at 20, the opposite is A and the hypotenuse is C. It's A over C. If I want the cosine of 20 degrees, you're looking at the adjacent on top and the hypotenuse at the bottom. Adjacent of 20 is our little b, and the hypotenuse is a c. Now, just keep in mind that my cosecant would be the reciprocal of sine. It would be c over a. And secant would be reciprocal of cosine. It would be c over b. They're there. They're in there. You just have to flip them over to get them. Okay, but I'm just focusing on SOHCAHTOA and TOA right now. And tangent of 20 degrees represents our opposite over our adjacent, TOA, T-O-A. SOHCAHTOA. So in the 20-degree angle, the opposite we already saw was A from sine, and the adjacent is B from the cosine. So it's going to be opposite A over the adjacent B. If you're looking at the 20-degree angle. But remember, we have 2 acute angles in this triangle. There are 2 acute angles. So I could actually look at the 70-degree angle as well. And I could find the sine of 70 degrees. The sine of 70 would be the opposite of 70, which is our B, over the hypotenuse, which is our C. B over C. Did you see that fraction somewhere else? Cosine 20, exactly right. Those 2 are equal values. Because, and we learned this before, we learned it in chapter 9. You might have forgotten. We did learn it in chapter 9 that the cosine of one acute angle is always equal to the sine of the complementary angle. So the cosine of 20 will equal the sine of 70, and it's only because the 20 and the 70 add up to 90 degrees if that happens. This just means we're switching angles in a right triangle. So guess what the cosine of 70 is going to be? What fraction is going to be cosine of 70? A over C. It's going to be the same as the sine of 20. A over C. So yeah, those would be the same. Sine of 20 would equal the cosine of 70. You're actually going to see that on your unit circle as well. You see that all over the place on the unit circle. Actually, I have it right here. You see it at sine of 30 is a half. Cosine of 60 is also a half. They're both a half because 30 and 60 add up to 90 degrees. So cosine of one angle always equals the sine of its complement. Works for cosine and sine. It always works for cofunctions. So cotangent and tangent it'll work for. Secant and cosecant it'll work for. But tangent of 70 is simply going to be the reciprocal of the tangent of 20. Cosine or tangent of 20 will be b over a. So it's the reciprocal of the tangent of 20. So these are complements here will be reciprocals. All right, just wanted you to access some of your prior things that we've seen before that we've talked about because it's going to come up in today's page. All right, so I've listed all the problems that we're going to do together as notes. If you look at that, and then when you get to be on your own, there's 5 problems that I want you to add to that paper that you'll show me before you get it checked off. It's these 5 right here. But I want to do these together with you. Doing those will help you do the ones that you need because 9 through 12 is just like 13 and 14. 29 and 28 and 29 is just like number 30. 44, 47 are just like number 45, and 50 and 53 are just like 56. So you'll have examples to do your 5. But we're going to do these together. All right, so let's start with number 1. And what it's asking us to do in number 1 is find the exact values of the 6 trig functions of theta in the figure. Use Pythagorean theorem to find the third side. So they give us an 8 and a 6 and a theta. So let's quickly sketch the triangle. 8's the bottom, 8's horizontal, 6 is vertical. So what they don't give us is the hypotenuse. We're missing the hypotenuse. Okay, so this is number 1 on your paper. We're doing these together. You should be working on it right now. You should have a piece of paper out. You should be writing these down with me. This is what you're going to show me and get it checked off. You don't want to do this later. Do this now. This is a new section. This is our next section in our book. And I wanted you to get a good head start of it. And it's basically based on SOHCAHTOA. So it shouldn't be a hard section, but if you're behind and not doing it with me, it's going to be very difficult to try to get it on your own or catch up. So right now, we know how to do Pythagorean theorem. 8 squared plus 6 squared equals c squared. We want to get this hypotenuse, which is our C number. And we can just square root both sides and put it straight into our calculator like that. We've been doing that all year. I'll just give you the answer. I know that if it's a 6 and an 8, then I'm going to have a hypotenuse of a 10. So C is going to equal 10. So that would be my hypotenuse number. And then it's asking us to find the 6 trig function of theta. Theta's right there in that bottom corner. That's what this one's asking us. See how they put theta right there in that bottom angle? They want us to find the 6 trig functions. And they want us to just make them fractions. So we'll just list the fractions right down here. Sine of theta is going to be the OH. So SOH. So it's the O 6, it's the H 10. Always reduce it, it's 3/5. 3/5. That means, arrow, cosecant theta is 5/3, just flipped over. If sine is 3/5, cosecant is 5/3. You just flip it over. That's 2 functions already done. Cosine of theta is AH, cos CAH. So it's 8 over 10, which will reduce to 4/5. And that means your secant, SEC, is reciprocal of cosine is going to be 5 over 4. You just flip it over. So there's 4 functions done right there, just the fractions. They wanted us to give you the fractions. Tangent of theta is going to be TOA, T-O-A. The opposite is 6, and the adjacent is 8. So we reduce that to 3/4. And that means cotangent, C-O-T, cotangent of theta, is the reciprocal of that, so it's 4/3. So you found the triangle, you found the third side of the triangle, and then you just do SO, cot, and TOA from that theta angle, the angle that's in theta.
This is about time you can let me know, but Miss Sobel is wondering if you could sign a card for Miss Sawyer.
Sure. Okay, let's get back to where we were. So that was number 1. Going to number 2. Not number 2, number 5. Okay, 5 has 2 triangles. So if you're on the link, you can zoom in, see the 2 triangles. It says, find the exact values of the 6 trig functions for the angle of each of the 2. And we're just going to do 1 trig function for each of the 2 because I just want to, it's only all we need is 1 to show you what's going to happen here. And explain why their function values are the same. So we won't even draw that one. Let's just find the sine of theta on number 5. So 5, sine theta. Sine of theta, and the first triangle is opposite over hypotenuse, which are the 2 they gave us. So they gave us the OH, it would be 1/3. So sine of theta is 1/3. And sine of theta in the other triangle is 2/6, which also reduces to 1/3. Why are they the same? Why are those 2 going to have the same sine, the same cosine, and the same tangent, and the same all 6 trig functions, when they're not the same triangle? They're different triangles. One's small, one's big. Why would their sine values be exactly the same? Because congruency is really close to what I was looking for. We used a word in chapter 8 of our geometry when 2 triangles or 2 shapes, any 2 shapes, had the same angles in them. We had a name for it. Start with an S. Similar triangles are going to have the same ratios. Okay, these are going to have the same trig functions because these 2 triangles are similar triangles. They have the same angles. If you got 2 angles in one congruent to 2 angles in the other, they're similar triangles. So what you're going to put down here is these are the same. You're going to have the same sign because the angles are the same. And the triangles are similar. That's why you're going to have all the same trig functions. So whenever you get 2 similar triangles, 2 similar right triangles, and you're doing SOHCAHTOA, TOA, your sine, cosine, and tangent are all going to be the same because the 2 triangles have the same angles. So it's like you're finding the sine of any 30-degree angle on any 30-degree triangle, and you get all these values across your chart are going to be the same no matter how big or small your triangle is. If it's a 30-degree angle in a right triangle, that means the other angle is going to be 60. That means all of these sine values are going to be there no matter how big or how small that triangle is. If it's a 30-degree angle, it's going to be similar to any other 30-degree right triangle angle. So whenever you have similar triangles, you're going to get the same trig functions. All right, 9 through 12. 9, it says sine is 3/4. And it says sketch a right triangle, use the Pythagorean theorem to determine the third side, and then find the other 5 trig functions. So did you realize that if they gave you just 1 trig function, sine of theta is 3/4, you could find all other 6 trig functions just by knowing 1. Because we know what SO means, S-O-H. We know that 3 is our opposite side and that 4 is our hypotenuse. We understand that from SOHCAHTOA. When they say sine of theta is 3/4, they're telling you two sides of your right triangle already. They're telling you the opposite of the angle is 3 and the hypotenuse is 4. So if I draw a little right triangle over here and I put theta in there, the opposite of that is 3 and the hypotenuse across from the right angle is 4. Is that enough information to find the third side? Yeah, we've been doing Pythagorean theorem all year. So this is like b down here. It's going to be like 3 squared plus b squared equals 4 squared. You're going to need to subtract 3 squared on both sides. And then you're going to want to square root both sides. So b equals, because those will cancel out, 16 minus 9. Can you do that in your head? Because 4 squared is 16, 3 squared is 9. Radical 7 is going to be our answer, right? It's going to stay in the radical. It's going to be a 7. Why do I not want a decimal? Because they're going to want exact answers here. You get an decimal, it's rounded. You don't want to round it right now. You want to leave an exact answer. So this little b right here is radical 7. So now sine, we know that cosecant, I'll put that in small letters underneath it. Cosecant is 4/3 because that's reciprocal. Cosine of theta we can now find because we know the adjacent side of theta is radical 7 and the hypotenuse is 4. But when you do secant of theta and you try to put 4 over radical 7, that doesn't fly. Not allowed to keep a radical on the bottom. So we got to get rid of that radical from the bottom. You got to multiply radical 7 on top and bottom. So your secant is actually going to be 4 radical 7 on top and a regular 7 on the bottom. You have to use the rationalizing your denominator to get rid of that radical from the bottom. So that's an exact answer for secant. So secant is this answer right there. Cosine is just the radical 7 over 4 because radical 7 can be on top, just not on the bottom. Your tangent of theta is going to be the opposite over the adjacent. So it's 3 over radical 7, which is not allowed. But before we fix it, let's flip it over because that would be allowed for cotangent. Cotangent of theta is allowed to be radical 7 over 3. But we can't leave the 3 over radical 7, so we got to fix that. So multiply radical 7 on top and bottom. You get 3 radical 7 on top and a regular 7 on the bottom. So tangent had to be fixed, but cotangent didn't. Because when you flipped over the 3 over radical 7 and got radical 7 over 3, that's fine. Okay, so that's 9. We may not do 9 through 12 because we don't need to do 4 of those, but we'll do at least a couple. Let's do 9 and 11. So let's just do 9 and 11 because that, I think, will give us enough information. I'm going to put 11 right below it. Number 11 is going to give us the secant is 2. But wait a second, that's not a fraction. I need two sides of my triangle, and that's just a number. Can we make that a fraction? Yeah, you can always put a 1 under anything and make it a fraction. What is secant as a fraction? Can you tell me? What is secant as a fraction? What is that? Because remember, sine is a fraction. Sine was the OH, so SOH. So what would secant be as a fraction? Good, it's hypotenuse over adjacent. Because secant is when you flip over cosine, and cosine is AH. So this is HA. So now let's draw the little right triangle with your theta. You've got H is 2, that's your hypotenuse, we know that's a 2. And you've got the adjacent as a 1. What we don't have is the opposite side. We're missing the opposite side. I'll put that as B. So we're going to need to do 1 squared plus B squared equals 2 squared. Subtract 1 squared on both sides and square root both sides, but leave our answer in the radical. So I need radical 4 minus 1. So that's going to be radical 3, right? Radical 3, because that's 4 and that's a 1. So 4 minus 1 is going to be a 3 inside the radical. So that's my little b side, is radical 3. So now I can get all my other trig functions. I know cosine of theta is going to be 1/2. That's going to be 1/2 because it's 2 over 1 flipped over. Sine of theta is going to be OH. O is radical 3 and H is 2, so it's radical 3 over 2. That means cosecant of theta is going to be 2 over radical 3, but that can't stay, so we got to multiply radical 3 on top and bottom. 2 radical 3 over 3 is our answer for that one. That was where we fixed cosecant. Cosecant cannot have a radical 3 at the bottom, so we had to fix that. But the sign was fine, radical 3 over 2. And then the last one is tangent. Tangent is TOA, T-O-A, so it's going to be radical 3 over 1, or just radical 3. You could put 1 on the bottom if you like it, or you can just put radical 3 if you like it. Either way works. Either way works. And then cotangent, we got to flip that over. So it's going to be 1 over radical 3, but can't have the radical at the bottom, so we got to fix it. You get radical 3 over 3. Now, I will tell you that we could have cheated on that. We could have looked at our chart. Could have looked right here. If y'all, I know you're writing it down, but if y'all look at my paper here for a second, just for 1 second. You see secant, and then you see a 2 right there. Secant is 2. Isn't that what our original problem said? Secant is 2. Where was secant a 2? It was at 60 degrees. Sine was radical 3 over 2, which we got. Sine is radical 3 over 2. And the cosine is 1/2, which we got because we flipped that over, got 1/2. Tangent was radical 3, which we got. Radical 3 over 1, which is radical 3. Radical 3 over 3 is cotangent. We fixed that one. And then we got the 2, and then 2 radical 3 over 3 was cosecant, which we got that one too. So we could have cheated and just looked across the chart and found where secant was 2. That doesn't always work. This just happens to be a common angle. This happens to be a 60-degree angle in there. Okay, that's not always going to happen. You're going to have different numbers, like on number 9, that wasn't a common angle. We had to actually figure all these out. But sometimes you run into some common angles that you could have just looked at your chart for. But just notice, it's always about a right triangle. Just because you see these things, numbers on the chart, just think they're just numbers. They're still all showing you a right triangle. Everything on here is showing you a right triangle. That 60-degree angle is this triangle right here, which makes all those numbers on the chart. It's always about the right triangle. All right, let's go to 28. 28 is next. Okay, that would be up here. Now, the reason I skipped over, the 17 through 26 is they're just asking you to fill in numbers on the chart. You could go down the chart and you could fill in all those numbers, and they're all on here. So I'm not going to redo that. You've already done that. You've seen the chart. You've seen the unit circle. They're all on the unit circle in the chart. Sine of 30, you could find how many radians that would be. You could find its function value. It's all right here. So if I'm looking at like number 17, 30 degrees, okay, that's pi over 6 in the radians. So I would just put pi over 6 for radians. And it says find the sine value, it's 1/2. It's all right there on the chart. Every single one of these is on the chart. So not doing that one again. You've already seen your chart and you've seen the unit circle. And this 33 to 42 box that we're going to work on in chapter 2. It's identities. We're going to work on those later. But 28 and 29 are good ones. It says sine of 30 is 1/2. Okay, so let's write the problem first. Sine of 30 equals 1/2, which it does. If you look at 30 degrees and you look at sine, it's 1/2. And then it says the tangent of 30 is radical 3 over 3. Tangent of 30 equals radical 3 over 3. So let's take a look at what they want. They want a cosecant of 30. So they want cosecant of 30. Mr. Beverly. Good, how are you? No, she's not here at the moment. Okay. All right, so they want cosecant of 30. They want the cotangent of 60. So letter B, they want cotangent of 60. Okay, so just put equals for each one. We're going to find each one. Cosine of 30 is C. And D, they want cotangent of 30. Okay, so let's see what we can find. Can you find A pretty quickly? Take a look at A. What's it asking for? Cosecant. What do we know about cosecant? Which one is it a reciprocal of? Cosecant is at the very end, and it's a reciprocal of the one at the very beginning. Is that we work our way out from the center. So cosecant is reciprocal of sine. Cosecant and sine are reciprocals. So if I know sine of 30, then cosecant of 30 has to be what? 2 over 1, which is just 2. Okay, so that's a 2 right there. Or you could put 2 over 1. Either way works. Okay, because these are reciprocals. I'm going to just put recip for reciprocals. Okay, what about B? Cotangent of 60. This is why I showed you 20 and 70 at the beginning of class today. That the sine of 20 equaled the cosine of 60, or 7, so sine of 20 and cosine of 70 were the same because they added up to 90. Tangent of 30 and cotangent of 60, don't they add up to 90 degrees, 30 and 60? So the tangent of one is going to equal the cotangent of the other, so they're the same. This is also going to be radical 3 over 3. You can double check it. It's on your chart right here. Actually, we can look at it on here. Look at, I got 60 degrees. Cotangent of 60 is radical 3 over 3. Tangent of 30 is also radical 3 over 3. They're the same. You can see right there and right there, they're the same. Tan of 30, cotan of 60, they're both radical 3 over 3 because they add up to 90 degrees. 30 and 60 add up to 90. Co-functions. Tangent and cotangent are co-functions. Sine and cosine are co-functions. Sine and cosecant are reciprocals. That's different. They're reciprocals, but sine and cosine are co-functions. Tangent and cotangent are co-functions because they both have the word tangent. Sine and cosine both have sine in it. Secant and cosecant are co-functions. They both have secant in it. But sine and cosecant are the reciprocals. And cosine and secant are reciprocals. Different than co-functions. Cosine of 30 is going to be what? Cosine of 30. Can we figure that out? For cosine of 30, we know that sine is 1/2, and this is radical 3 over 2. Doesn't sine mean OH, opposite over hypotenuse? And doesn't this mean AH or OA, like right, opposite over adjacent? So let's see, cosine would be AH, would be 3 over 2. No, it's not going to be 3 over 2 because we had to fix this one to get it to be radical 3 over. Cosine of 30, you can actually see it right here on your unit circle. Cosine of 30 is radical 3 over 2 right here. So it is our radical 3 over 2. We already actually saw that triangle, and if you remember that triangle from before, it was right down here on number 11 where we had the 1 and the 2, and then we had the radical 3 for the opposite side. So opposite side was radical 3 over 2. In this case, radical 3 happens to be the adjacent side, so radical 3 over 2. So that works there. And then tangent of 30 and cotangent of 30 are reciprocals. So this will be 3 over radical 3 when you flip it over. If you multiply radical 3 on top and bottom, you get 3 radical 3 over 3, which cancels out and just leaves you with radical 3. That just leaves you with radical 3. So those would be your other 4 pieces. Let's go to 29. 29, they're giving us the cosecant is radical 13 over 2. Cosecant is radical 13 over 2. They're just giving us clues. So we know that hypotenuse is radical 13 and opposite is 2. If we were going to draw a triangle, they've given us 2 sides of the right triangle, because trig is all about right triangles. And if they're giving me one trig function, then they're giving me 2 pieces of the triangle. So cosecant is radical 13 over 2, so I know h and o, because that's reciprocal of sine, and sine is OH. So this is HO. And then they're also giving me secant is radical 13 over 3. So secant is radical 13 over 3. It is theta. Yeah, it's theta. Okay, so that actually works out really well, because secant is h over a, hypotenuse, which we already knew the hypotenuse was radical 13. And then now we've got our adjacent right here. So you could actually find, you have all 3 sides of your triangle now. So we could actually find the 4 pieces that they want pretty quickly. They want sine, cosine, tan, and then secant, 90 minus theta. Let's write that down. So A, they want sine. B, they want cosine. C, they want tangent. And D, they want secant of 90 minus theta. And I'll show you what that means in a minute. It's much easier than you think. It's much easier than you think. Let's look at sine. So if we want sine, you know it's OH, right? So SOH. So you could just find the O, you could find the H, but if you know cosecant, just flip it over. That's your sine. So it's going to be 2 over radical 13, which we can't have, which is going to end up being 2 radical 13 on top and a 13 on the bottom. You're going to multiply top and bottom by radical 13, and you'll end up with 2 radical 13 on top and a regular 13 on the bottom. Cosine is going to be 3 over radical 13. And you're going to fix that. To fix it, you basically just put the radical on the top with whatever number's there. So 3 radical 13. And then just take the radical out and put that number at the bottom. That usually happens every time you want to fix a radical. Just put the radical number at the top next to the number that was already on the top, and then bring the radical out and put it on the bottom. That works every time to fix a bottom radical. Tangent would be TOA, T-O-A. O is 2 and A is 3, so it would just simply be 2/3. That's the opposite over the adjacent. That's TOA. They gave us the opposite of 2, they gave us the adjacent of 3, so we can just make a fraction out of it. Now secant of 90 minus theta means secant of the complementary angle. Secant of the complementary angle. Because 90 minus anything is its complement. When you take 90 minus 30, you get 60, which is the complement of 30. So complementary angles are the same as their cofunctions. Sine of, we said that up here a second ago, cotangent of 60 was the same as a tangent of 30. Those ended up adding up to 90, and they were cofunctions. So the secant of 90 minus theta is going to be the same as its complementary angle with secant. With cosecant. Secant is going to be the same as cosecant. So it's going to be radical 13 over 2. The cosecant of one angle is going to equal the secant of its complementary angle. These two are cofunctions. Just like I said, the sine of one angle is the cosine of its complement. Cosecant of one angle is the secant of its complement. So those two would both be radical 13 over 2. So this would be like 20 degrees. This would be like 70 degrees. Cosecant of 20 would equal the secant of 70. They're complementary angles, they're called. Okay, let's go to 44. 44 is tangent of 23.5 degrees. Okay, so this is a calculator. Oops, don't need it that big. We got a calculator problem here now. Tangent of 23.5 degrees. That one's not difficult because there's nothing special to do about that one. But what about letter B, which is cotangent of 66.5? Cotangent of 66.5 degrees. Okay, so this is your A, this is your B. Let's go to Desmos and check it out. It's just calculator. This one is not one that you have to figure anything out of. You just have to get the calculator. Scientific. Okay, so tangent, you can just go straight to tangent. So tangent 23.5. And you can look at it, and it shows it to you right there, 0.4348. Let's just put that in as 0.4348. Now, cotangent doesn't have a button on your calculator. If you look at Desmos, and you got sine, cosine, and tan, you go to the function buttons, and all you have is the negative ones. You don't have the reciprocal functions on here. There's no cotangent, there's no cosecant, there's no secant. So how do we put those into the calculator? And it's very simple. Cotangent is the reciprocal of tangent. So if this was tangent over 1 and you flipped it over, it would be 1 divided by tangent. So the reciprocal of tangent is 1 divided by tangent of 66.5. Ooh, why are they the same answer? Why are those two the same answer? 0.4348. So 0.4348. What do we know about 23.5 and 66.5 if you add them together? They're complementary angles. They add up to 90 degrees. The tangent of 1 is going to equal the cotangent of its complement. But to put cotangent in a calculator, you can't put cotangent itself. You actually have to use tangent, but it's 1 divided by tangent is the same as cotangent. Cotangent is the reciprocal of tangent. So if you've got tangent over 1, you flip it over, you have 1 over tangent as your reciprocal. So that's how you plug in cotangent. You do the same thing for secant and cosecant. Let's go to number 47. 47. Here's some good ones for you now. Secant of 42 degrees, 12 minutes. Secant of 42 degrees, 12 minutes. What would that be on a calculator? What is that minutes thing? Wait, minutes? I thought minutes was time. Why is 42 degrees, 12 minutes there? Interesting. Because that's what it says up here in number 47. It says secant 42 degrees and then 12, and it has a 1 tick mark, which is minutes. What are minutes? That's important. Something that, especially if you are navigating in airplanes or ships, and you're telling somebody to go a certain amount of degrees, and maybe you tell them to go 42 degrees 15 minutes instead of 42 degrees 12 minutes. It may not make a whole lot of difference if it's a short amount, but if they're doing the wrong degrees for a long period of time, you're going to end up a long way off. Okay, this is what you would break each degree into. Now, you got to see if you can catch this mentally. You know how small 1 degree is? Like, you look at the whole circle is 360 of those degrees, right? 1 little degree is really small. If you break that degree up into 60 pieces, microscopic basically, those are minutes. Those are minutes. So 1 little degree is broken up into 60 pieces because there's 60 minutes in an hour, just like there's 60 minutes in a degree. So 1 degree can be broken up into 60 little teeny minutes, like microscopic minutes. But each little minute, which are microscopic already, can be broken up into 60 pieces called seconds. That's even more microscopic. I mean, you really would have to be microscopic to see the seconds. So you'll see the 2 little tick marks mean seconds. Now, how do we figure this one out? Well, to get this on a calculator, we got to get a decimal out of it. Got to get a decimal out of it. So this is actually 12 minutes, which we know there are 60 minutes in every degree, or 60 minutes in an hour. So 60 minutes in a degree. So what I can simply do is divide that by 60. Secant of 42 degree, or 42, and I can put 12 over 60 in my calculator. So 12 divided by 60 in my calculator is 0.2. So it's going to be 42.2 degrees. Now to put this in my calculator, it's 1 divided by cosine of 42.2 degrees, because secant button is not there. So, but cosine button is there, and secant is the reciprocal of cosine. Secant is the same as 1 over cosine. So if you go to your calculator and you put 1 divided by cosine of 42.2 degrees, you'll get that 1.3499. 1.3499. That's the same as secant. 1 divided by cosine is the same as secant. So 1.3499. 1.3499. We'll just do A on that one for now. Just wanted to show you what minutes were, and then you would also have seconds too in there. And so cosecant, you would just put 7 over 60 and get a decimal, and then put 1 over sine for that B. We won't do B at the moment. Let's go 50. I guess I wanted to do one with seconds, so we'll just do A. Secant 56 degrees, 8 is minutes and 10 is seconds. 56, 8, 10, and it was secant. Okay, so number 50 would be secant 56 degrees, 8 minutes, 10 seconds. Okay, we need to get that into a decimal. Only way to get that into a decimal is take 8 and divide it by 60 minutes. There are 60 of those minutes in a degree. What do you think we multiply the seconds by? So if you were counting, you're super bored in my class and you really were just counting seconds, trying to get out of here because it's just so boring. How many seconds would you count in the hour? How many seconds are there in an hour if you just counted seconds? There'd be 3,600 seconds, 60 times 60. 60 seconds in a minute, and then 60 minutes in an hour. So there are 3,600 seconds. Oops, that's not a good zero. 3,600 seconds in 1 hour, or in 1 degree. So think about that tiny little degree broken up into 3,600 pieces. Can't even think about it in our minds because it's so small, but it could happen if it was microscopic. So in your calculator, you'd put 10 divided by 3,600, which is 0.003, we'll call it, 0.003. 8 divided by 60, 8 divided by 60 is 0.133, or 0.13, we'll call it. And then we have the 56. So 56 is the whole number, 0.133, because the 1 and the 3 would be under zeros here, because if you put the 013 like this, you're going to get 0133. So your decimal is actually 56.133. You get the 1 3 from here, and you get the last 3 in the third column there. So 56.133, if I want to put that in my calculator, it's 1 divided by cosine of 56.133. You just got to put that straight in your calculator just like I wrote it. 1 divided by cosine is reciprocal of secant. So 1 divided by cosine, 1 divided by cosine of 56.133. And you'll get your decimal 1.7945. So 1.7945 is what you get there. So I wrote how you would put it in your calculator. And that's how you put those in your calculator. So it was 50, and then there was one left, was 53. And it's just asking you to use your chart. So 53 is not asking you to use a calculator. It says without the aid of a calculator. So 53, they want to know, they want you to find the right angles. This is like inverse. It's like using the -1 buttons. If sine of theta is a half, so if I went to Desmos and put inverse sine of a half, inverse sine of 1/2, you're going to see that it was a 30-degree angle. Okay, but we could actually find that on our chart, because you could look at your chart and you could look at the sine column and you could see where it's a half and it's 30 degrees. So you actually can find angles now on your chart if you know their values. So sine is a half at 30 degrees. So for number 50, what was it, 53, sine theta is a half. Where are we at down here? So 53 sine of theta equals 1/2. And then you're going to, underneath here, you're going to put theta equals 30 degrees. Or you could put pi/6 radians. Same as 30 degrees. They just want the angle. They want to know what's theta if sine is a half. What theta is when the sine value is a half. What would that angle be? That was letter A. Letter B says, for number 53, letter B says cosecant is a 2. Well, we already know it's the same because sine and cosecant are reciprocals. So cosecant would be 2, also at 30 degrees and pi/6 radians. So cosecant theta equals 2 at 30 degrees or pi/6 radians. They're both the same. Pi/6 is 30 degrees. All right, unfortunately, you don't have time to do your 5 today. I would have liked to have time, but we ran out of time because I had lots of interruptions there. But